Hi everyone, welcome to the Friday session before lunch. Maciek is going to be speaking to us about the inner mysteries of PyPy, how it runs our programs. Take it away.
Hi, I'm Maciek, and I've been developing PyPy for the past 8 years or something, starting with Summer of Code, and I run a small consulting business at Baroque Software. We've been working a lot on how to make PyPy and make running dynamic languages more usable to the user, so more understanding of performance, and this is what this talk is going to be about. I'm originally from Poland, living in the beautiful city of Cape Town these days. We're going to talk how PyPy runs your programs, how you can sort of go have a look what's the performance of your programs, and why a lot of folklore about what performance is and how it matters is actually not true, ideally. So PyPy, what's PyPy? Who heard about PyPy before? Almost everybody. So I'll just show quickly. PyPy is, I'm using a virtual env here, so my Python is a bit different. It has 4 here. It has 4 instead of 3. That's the major difference. And it's a different interpreter of Python, but normally does the same stuff. Well, it's Python, print 3. It uses magic to run code faster. So if you run stuff like from test import Pystone, I think, print Pystone.pystones, it's 1.49 million of Pystones per second, which is a bit faster than CPython. But what's interesting is if you run this again, it actually increases. So that's why most of the time. And then we have we have working network. I'll show you the website once it loads. On average, and like be always aware that averages are not always good, it's about 7 times faster than normal CPython, the one that you run. But again, there will be some more details later. So PyPy, it's normally you can run your Python programs. It's open source. It's under MIT license. You can incorporate it in anything you do. It supports x86, 32 and 64-bit, and ARM. So you can run it on Raspberry Pi. It's Windows, OS X, and Linux these days. And we are porting it to PowerPC and a mainframe platform out of all the things. Most people who use PyPy use it for long-running programs, specifically because, as I showed, it kind of like requires a bit of time to warm up. It has problems with C extensions. So if you're running a lot of code that uses CPython C API, don't use CFFI. CFFI is amazing. CFFI is a great way to call C. A lot of libraries work. So like often there will be a library that is there, like LXML, and there will be LXML CFFI, which will work using CFFI and not CPython C extensions. Who wrote a CPython C extension here? Good, don't do it. It's a terrible experience. Also use virtual env. It simplifies the installation. PyPy, you can either download it or it should come on your distribution. Virtual env, great idea. It's like deactivate now my Python is normal Python, and then I can say work on PyPy vmprof, and then my Python is a different Python. Libraries are separately installed. It's a great idea. Use it. So what does PyPy do to run programs faster? It's called a just-in-time compiler, which means that it takes, like, if you look at I have a incredibly sophisticated program here. It counts numbers. And if I do, where am I? Yes, I can do a program apparently. If you look at the function, this is the disassemble of the Python instructions. So normal Python interpreter would take those instructions one at a time and execute them. So there's a gigantic dispatch loop in C and saying, what's the next instruction? It's a load constant. Okay, I'm going to find that constant, put it on the stack, and look, what's the next instruction? It doesn't do anything more advanced. So like each time you execute the interpreter loop, it has to go find the bytecode, think about it a bit. What is it? Go to the correct place, and then execute the code there. What PyPy does is it will take this bytecode and replace it under your feet with an assembler. So if I run this function, can't use Mac apparently. If I run this function a lot of times, I use time to run it, it will like take 0.1 second. And if I use normal CPython for that, it's maybe too many numbers here. Let's decrease it a little. So that took 0.4 seconds, and PyPy here took like 0.06. This is obviously a very easy example for PyPy because what it does is it takes, this is just arithmetics. Like C compiler here would just throw your loop away and say, this is the number you're counting to. Like, don't worry too much. PyPy doesn't do that quite yet, but it's a simple arithmetics. It really compiles it to like a bunch of assembler instructions and then check if you didn't press Ctrl+C to handle the exception. That's essentially it. Now, what happens is that it will run the code in the interpreter for a while. So it takes a while to warm up. If I have like other program, I'll show you the details later. It does the same thing in a loop a couple times. So you can see that like loop here, the first iteration, scroll, 70 milliseconds, next one's 126, so it like tries to figure out compile to assembler, compiling to assembler is slow, and then speeds up as the time goes. Most of the time your programs will run faster, not always, and there are some issues, but typically if your program is written in pure Python, not in C, you can complain, and if it doesn't run faster, it's considered a bug. There's a lot of heuristics that optimize for what we call typical Python programs. What's a typical Python program? Nobody knows. So we are trying to optimize for stuff like common law, open source libraries, things people report about, which means that we're going to have trade-offs. Like we're going to assume that classes are not defined at runtime all the time. If you're defining classes at runtime all the time, you probably shouldn't do it in the first place because, well, it makes it really hard to read, but also makes JIT very confused. So those cases will be slower. What it really does in more detail, you take the Python code, you first run it in the interpreter mode, but like slowly dispatching the loop. So I'm going to take my example. I'm going to run it 1,000 times. Because now it finishes like really quickly, right? It's probably mostly just interpreter startup time. I'm going to put it in a gigantic exec. So each time it executes this code, it has to start from scratch and exec new code. So I'm not doing any optimizations just yet because each time is a function run only by 1,000 times. That's still relatively fast. Let's increase the number here. Okay. So that takes about 1.4 seconds here on this machine. I can repeat the experiment to see if it really does. Then when you hit the magic number, I think it's 1039 or something of loop iterations, it's the first prime number after 1024. I remember that. I don't remember the exact number. It runs this special mode that records the records the operations and compiles to assembler, and that's really slow. So if I run it 1050 times, which crosses the threshold, it's going to run a lot longer than 1.4 seconds, because now it warms up. So it's 8 seconds. I'm going to decrease the number here so we don't have to wait that long. So that's like 0.8 seconds, 0.7 seconds. Okay, but then, so it's about a couple thousand times slower than just one iteration. Takes like 10,000 iterations to record all the things, do optimizations, and compile to assembler. But then you compile to assembler, and then everything goes really fast. So if I add like an order of magnitude of iterations here, the runtime doesn't change at all. Like suddenly, like the optimized version just flies. Okay, so what I said is that it looks at what interpreter does bit by bit and then records what happens. But it means that some paths are not taken. Not in this example, but if I say so every third iteration, we do another count, let's say. I'm going to run this for like 1050 times. Okay, it will do the same. It will like sit and optimize, but then if you happen to hit this path, you're going to exit the assembler, jump back to the interpreter, interpret for a bit, and jump back to the assembler at the next loop iteration. So you're going like, this is the trace through your code, and then you're going to go hop back into interpreter. Okay, but that's inefficient because you're changing the modes, and that's really slow. So if you hit it 200 times, you're going to compile this path to assembler. It doesn't have to be a path in the, like here is the path in the source code, but it can also be a different type. It assumes types and say, if every 3 iterations you're going to have a string instead of an integer here or something, then you're going to take a different path too and exit the assembler. That's why we managed to optimize stuff out of it. What time do I have? What time do we start? 11 or?
You still have maybe half an hour.
Okay, cool. So this is what I did. Like you gonna go and take the small example and see how it's optimized. So if you see, I'm gonna run the VMprov demo and look again. Hop, hop. You can see that like the first iterations take long, but then it goes faster, 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 which means it finds more and more paths through the code that can be optimized away, and then at the end produces assembler code that covers the whole program. So when can I say my program does warm up? My friends recently wrote a paper that say it's a very difficult question. We don't know. What is a warm up? It turns out that JVM, for example, would start, then run faster, and then slow down again, for example, for some reason. So just run it long enough, see how it works, and run it long enough. Here it reaches eventually, it stabilizes around 3-point-something milliseconds. But as you can see, like here's a peak that says, okay, I did figure a new path, and now I have to optimize it, and it takes a while. So the strategy that I described is called tracing JIT. It has been tried with success and with less success. The less successful one was the Mozilla tracing JIT, and they eventually abandoned it in favor of method JIT, which just takes a function and compiles one function at a time. The more successful one is Lua JIT. Lua JIT is crazy fast, for example, if you like Lua, because otherwise it's a bit useless. But it's a masterpiece of engineering. Like for small language of Lua, it has, for example, almost no warm-up time because the interpreter is written in carefully crafted x86 assembler. Like Mike said at some point that the post is still findable, that for him, the compilers are just not good enough. Like they don't produce good code for what he wants to write, so he needs to write an assembler. So LoaJIT is a good example of tracing JIT that's really, really quick. So it does that has three modes in a sense. It does like swap one mode when it discovers that a loop or a function call or something becomes hot, then records the list of operations, then this list of operations becomes optimized away by like assuming a lot of things, and there are guards. Guards mean that like make sure that this thing does not change, or make sure that the class is correct, make sure that something is constant. And then those guards, when they fail, you go back to the interpreter unless you do this enough, and then you compile the path. Repeat, repeat, repeat. Machines are fast these days until you end up with an optimized assembler. So performance. I'm gonna talk now about how do you measure performance, how do you go ahead and improve the performance of your programs. So first thing that a lot of people actually fail at is you need a metric, you need a number. It can be latency, it can be number of requests. Ideally, it's just time it takes to do something. But you cannot optimize by just looking at the code and thinking, that thing should be faster if I write it that way. No, 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 no. Modern computers are way too sophisticated for this. It's good if your benchmarks are, the smaller the better, essentially, because your iteration time is very low. Like, if it takes a day to run your benchmarks, well, then you need to wait a day after each adjustment. How many can you make? Not that many, one a day. If it takes 5 seconds, how many adjustments can you make? A lot, as soon as you can type. Another very, very important point is that it's very important to be able to repeat stuff. So measuring stuff in production is good because it gives you the data that actual users go and use, but it's not very repeatable. You can go ahead and ask those users like, hey, all Facebook users, can you post again the same messages at the same times because I want to measure our changes. So it's good that if your benchmarks are repeatable. The usual optimization quote is that there is 80-20 rule, and 80% of the time will be spent in 20% of the program. And that's great if you're in the 70s and your programs are 100 lines of code. Then you can just read those 20 lines and fix them. But in this day and age, we are running like multi-million lines projects, and then 20% of million is still 200,000 lines of code. That's a lot of code. That will, yes, that's the majority of your code, a majority of the time, but still not a tiny thing. So you need to identify the slow spots, and sometimes it comes with strange answers. I'll show you a few later, but identifying the slow points and optimizing them is the usual thing. So Guido has points about optimizations. Can anybody see that? No? How do you zoom in? Like that. Ah! So I'm going to read it. Avoid over-engineering data structures. Tuples are better than what? I love Google+. Tuples are better than objects. Try name tuple 2 though. Prefer simple folds over getters to their functions. Built-in data types are your friends. Use more numbers, strings, tuple, lists, sets, dicts, and also check out the collection library. Be suspicious on function method calls. Creating a stack frame is expensive. Don't write Java or C++ or JavaScript in Python. Are you sure it's too slow? Profile before optimizing. The universal speedup is writing small bits of code in C. Do this only when all else fails. So, I agree with those two. Check what you're optimizing and don't write Java in Python or otherwise. But the rest, you have to think like, okay, don't do this, don't do this, don't do this. But what you're going to replace it with? Be suspicious of functions and method calls. So don't use functions, use what instead? Spaghetti code with tons of ifs? That doesn't sound like a win at all to me. tuples are better than objects. Well, did you ever end up with like a 7 tuple and like which index did I put this stuff in? I don't remember. Maybe 3, maybe 4. Names are good. So the good part is that because PyPy is an optimizing compiler, those optimizations are unimportant. Like, they actually make stuff slower. Function calls, if they're small, they will get inlined and removed completely. Objects are as fast as tuples. Like on PyPy, objects generally use the same strategy as V8 for hidden classes, which means that your objects are as compact if you're not using slots as if you're using slots. So slots don't do anything. You keep compact objects and they're as efficient to use as tuples. So those things are just unnecessary in PyPy because PyPy can optimize those things away, and then we can happily forget about optimizations that cost us readability. And the last one is, I don't even know, the universal speedup is rewriting small bits of code in C. Well, really? Like, do you want to rewrite like 200,000 of your code in 1,000,000 lines of C? Like, if you say have problems with twisted, would you like to rewrite twisted in C? I definitely would not. So, as I said, we are here because those points don't really work, not very well. There are trade-offs between productivity and performance, and we ideally want to avoid those. Also, like the thing that we've been seeing a lot is once you fix the obvious mistakes, like you were using wrong algorithm for something, profiles either tend to look flat or they point you to things that gives you incredible hindsight but nothing more, like you shouldn't have used Django ORM. Well, thank you very much, but it's not helpful because I cannot just swap the ORM for something else in this gigantic project. So let's look at some profiles. Like I wrote a small example here, or a medium-sized example, let's say. I'm not gonna optimize it, but it's online, so I'm gonna go and show you. You can just go and optimize yourself. I would be very interested to see how it goes. So the idea is that it does stuff like parses things that are either Polish notation or reverse Polish notation. I never remember. It parses strings like +2, 2. Is the reverse or a normal one? Anybody remember? Normal Polish, okay. And then what it does is generates a random ones. Here we generate a random string, and then we try to use the oracle to guess what number it produces without actually checking. So we are adding and subtracting 1 at the end to see when it ends at 0, essentially, because the only thing we have is an oracle that gives you, is it bigger than 0? Exercise. Like, it doesn't do anything useful. So we have a tool called, oh yes, a worry about timeit. Never ever use it. Timeit is a bad thing. Timeit does show you a minimum number. So remember the thing when I showed you warm up, how it like went like 130 milliseconds, 20 milliseconds, 8 sometimes. So timeit would show you 3. Thank you very much, but this is not true. Timeit also disables the GC. Who disables the GC in their production? Well, then why would you disable it during benchmarks? Because you're suddenly measuring something else than you're running in production. Never use timeit, just ever. It's a bad piece of software. I will write a long blog post or give a talk, maybe not a talk, it'll be boring, but I'll write a blog post why timeit is a terrible thing. So we wrote a tool called vmprof, which is a statistical profiler, and shows you graphs like that. So you run it. Haha, I will not show you how we run it because I have incredible hindsight and I first took the Mac here and then forgot to port my software to Mac. So I will do it as soon as I get some time, maybe this weekend, but it doesn't work on Mac just yet. So what it does is it shows you run Python -m vmprof essentially, and it will upload the profile somewhere. And it looks like this. This is showing the split in PyPy between JITted, which is green, red, which is interpreted, and yellow, which is being warm up. So this means there's too much warm up. I run it for longer. This is another profile where I run it for longer. Again, jitting a lot. And again, this is the one where it's at least already jitted mostly. And there you can see that like most of the time it's spent in the Oracle and especially parsing. So when I tried it, I rewrote the parser to something else and got like 10 times speed up. But it shows you like that high-level problem is there, not a micro-optimization that you need to do in order to do something because it won't help. Like I have a profile here of Django admin. Django admin is incredible. Like you do 30 requests a second these days, and it takes like, here you can see it's like tons of calls. That here's a wrapper, that's a wrapper to a wrapper, that is in a wrapper, and then it checks has permission, and this has permission checks if the user has permission to view the website. It takes 90 million operations on the CPU to check if user has permissions. Why? I don't know. But this is a good example of a profile. Like, how do I start profiling that? Like, it's just tons of things that call each other. So yes, and this is exactly the case where the answer is don't use Django ORM, or don't use Django templates, which is not an actionable item. You can't really do that at Django admin, not use Django ORM. But maybe you can do things like cache has permissions. At the end, the comparison of a session key to something. So maybe you can cache that and just ask if this user already was notified of the permission, and that should take like big lookup, so about 15 CPU instructions and not 90 million. That sounds like a win, and that's already 20% of the total code. So this is VMProf. We are slowly running out of time, right? So I'm just going to quickly say what I do. I'll not go into details, but I run a small company called Baroque Software. We write VMProf, we are PyPy, we write a lot of stuff. And we do consulting mostly because monetizations of open source is a difficult question. So if you're interested in running your software faster, talk to me, generally speaking. And especially if you're interested in like expanding with VMProf. Questions?
Questions?
This is just a quick question for a common use case. Hopefully it'll maybe help people to hear it. Would, say, a application running UWSGI under Nginx benefit from PyPy?
It vastly depends what the application does. Like, if all it does, it sits idle waiting for network to do something, then unlikely. But if what it does is crunches some numbers, and like that usually means shuffling strings around, that should benefit. Like what we've seen in production for stuff like their posts on baroquesoftware.com on blog. So UWSGI guys paid us to do the embedding API, and they're using PyPy everywhere. So that should probably answer the question, I guess. They said they're like over half their deployment is on PyPy these days.
Anyone else?
Now that you have a Mac, will we get things like VMProf without having to wait a few months?
Apparently, because I need to use it.
There's been a lot of interest in the sort of scientific Python, pandas, scikit-learn set of software. Does that play nicely with PyPy?
So we do have an implementation of NumPy that's mostly complete these days. We do not have an implementation of SciPy or pandas working on PyPy. And there has been quite a bit of a problem. What's going on? Yes, no. So the problem seems to be along the lines like if we want to, like, PyPy does play well with numerical stuff. If you do stuff like you go in a loop and add numbers from NumPy arrays, it's really quick. What we said up front is like, in order to do anything useful, we need to somehow deprecate the CPython C API and provide other means of calling C, like CFFI. CFFI has been blazing success. It's one of the more popular packages on Cheese Shop. It sees over 1 million downloads a month. It's working. People are using it. Numeric community said, no, we need CPython C API. We need exactly that API that's there, and we're not going to cooperate with that. And that's essentially a deal breaker because we're not going to port everything. We need a story, but I'm not sure what the story is and where we fit in. Like, we really, it's the same for CPython and writing JITs for CPython. Like, the CPython C API is why Unladen Swallow failed. It's why Python will probably fail, because you're running into limitations of an API that prevents you from doing proper garbage collection, prevents you from doing anything with the GIL, prevents you from doing a lot of things. So we need to somehow arrive at the position where we can deprecate that API. That leaves way too many abstractions to the user of the API, and most users are not writing directly in it. Most users will use Cython, will use Swig, will use some other mechanism of generating this binding. So we need a story to somehow get rid of CPython C API in order to cooperate with the numeric community, or for them to have some interest. They have been very hostile to our efforts, to be honest. Like, I have no idea why. It's another tool. But I think they perceive it as a conflict of interest, say, between us and, say, Numba people who are trying to write a JIT for small specific snippets of code in Python that has to be numeric and can abandon some of the semantics. So, I don't know. It's a difficult question. I would love to see some effort in that way. But so far we focused on other stuff, like all our customers, like commercial customers, and all our PyPy deployments are essentially websites. Like, there are some sophisticated websites that do various kind of privacy invading user tracking or high frequency trading or stuff like that. Well, high frequency tradings are not websites per se, but those sort of use cases are not directly related to numeric software.
What's the compiler underneath? Your Cython and PyPy. They're all written in C, and then you are using the GCC compiler, or what's the difference?
PyPy is not written in C. PyPy is written in a very strange language that looks like Python and can be run by Python, but it's not Python. And that language is statically typed and compiled to C. I would not recommend this language to be used by anybody other than compiler authors, but for writing compilers is great, but that's it. There has been efforts, like I specifically omitted this from the talk, but there has been efforts by other people to reuse the same toolchain to write other interpreters. Like the more successful one's Pixie, that's a sort of Lisp interpreter, and that's written in our Python and uses our garbage collector, our JIT. There's PyKit, which is a Rocket interpreter. There's a bunch of research around that area. So we use different stuff. We generate C out of it, and then compile it using GCC. But in theory, we could generate LLVM or directly assembler if we were feeling particularly adventurous. Like, we generate something out of it.
So PyPy uses a different, there are slight differences between what PyPy interprets and what CPython interprets.
No.
Correct? No.
No, that's just our internal implementation language.
Oh, okay.
That you don't have to see.
Okay, maybe I misread your website then. All right.
No. PyPy, as I shown, like PyPy runs a lot of Python software, like virtualenv, pip, Django, like all this stuff will run on PyPy. You might need to swap a database driver for a different one. The one uses CFFI and not CPython C extension. But PyPy generally runs Python.
Okay, so the main things that people have that cause conflicts with PyPy are things that use the C extension rather than CFFI. Is that?
Yeah,
okay.
that's the main problem usually. We have support for a subset of CPython C API, but it's slow because we have to emulate ref counting, all the details of CPython we just emulate because it leaks all the abstractions. So we carefully emulate that, and that takes forever. And it's not complete, but it runs some extensions.
Just to follow on from the question about the SciPy and so forth. So there's no technical limitations to the CFFI interface as compared to the CPython one. It's really just a kind of politics kind of thing.
Yeah, so the main difference is that CFFI uses, you write your code in Python and not C, right? So if you have a C extension, you write some logic in C, like you write py incref a bit all over the place, and then there's one place where you forget and segfault. No, this is how it typically goes. On the exception path, which you don't test, for example. While CFFI, you run stuff, it's a bit like C types, except smarter, but you run stuff from Python and not from C. But there are no technical limitations on calling C. There are some issues with calling C++, because then you need to wrap C++ in a C interface, which is annoying. But there are no real, it is politics, but it's also like a giant code base, and like what we do with that, it's a lot of politics. And also like those people are running consulting company that rewrites code to C for money. So
they have a vested interest in.
I don't know how much, to be honest, but there might be some vested interest in not having a solution that solves. I guess PyPy doesn't solve all the problems, but it solves a lot of problems for cheap. Like PyPy will not be as fast as a custom written C solution, but the cost of getting there is much, much lower. Like you just swap your interpreter and it works. If you get just 2 times speed up and not 4 times speed up, and you need that, then you might need to like go and optimize stuff, but you get something for free. I don't know, maybe I'm speculating. I don't know. I think a lot of issues are around, we have this gigantic code base, this is how we do things, this is how we've done things in the past, we can't just abandon CPython C API.
Okay, I think one last question, and Bruce can set up.
I see your interpreter there is Python 2. Python 3?
There is PyPy 3. It supports Python 3.2, which nobody wants to use, and no. I've seen statistics. Like if statistics are correct, so the Python 3 is mostly roughly like 5% of all downloads from Python package index. So PyPy is like around 1%, and Python 3.2 is below 0.5%. So PyPy 3.2 would be 1% of below 0.5%. That's like 5 users that can do whatever. There is a plan to make PyPy 3.3 work and like release it. There are some performance issues though, like we need to re-enable optimizations, port them, check why things are not exactly how they're supposed to be and stuff like that. There hasn't been much effort because PyPy is this dual project where Python interpreter is one thing, and like the majority of deployments on Python 2, and then the JIT and everything is worked separately. So like each improvement to JIT benefits both automatically because the way it's structured. So I've been working a lot on warm-up improvements, on using less memory, stuff like that.
Great, let's thank Maciek.
Thank you.